is Q mean. At point A is our Q max. At point B is neither Q max or mean. Okay, is just a certain value Q. Okay. So the question now lies to us. Okay, before I go there, why they pick point A, point B, and point C? Because at point A, right, you have what? Q max. At point C, you have Q mean. At point B, the thickness is 20, not the smallest, but it's small enough. But you have what? You have your first moment of area. Okay, so we don't know where Q max or where tau max will occur. Remember what I tell you all, the most important thing is the what? You have to analyze based on the Q over T what? Ratio. Okay, so over here, where is Q over T ratio maximum? We don't know. That's what I want to find out. Okay. Now come to a question like this, we don't immediately rush, right, to find V over I, right? What is given to us? It is what? What is given to us over here? It is the tau max. Did they give us the V value? No. Okay. We can find the I value, but it's going to be tedious. It's not impossible. It's going to be tedious. Yes or no? Okay. So more important is the Q over T ratio. Okay. So now the thing is this: we are given tau max, and tau max is equal to V over I, right? And we're going to find our Q over T ratio. Okay. So knowing our Q over T ratio, okay, that was, so we have to determine position of tau max. Only after determine the position of tau max, then after that, you can find the V over I ratio. Okay, which is a constant, right, at point A, point B, and point C. Then after that, then you can find the shear stress at point A, the shear stress at point B, and the shear stress at point C. Why? Because you have the V over I ratio. Okay, so let's start doing it. So for all the cases, we first have to determine what is our, we have to determine what is our Q. Okay, T we know already. On the table, we already know what is our T value. Okay, okay, so now let's find our, so I'm going to call this our transformation. This will be our Y, Z, rotation about X. Okay, so we are going to find our Q, Z at point C first. Okay, so point C, we are going to consider this area. Okay, so the width is 30. The depth is 10. Okay, let me see again. The width is 30 because 50 minus 20 is 30. The depth is 10. The Y bar is what? 30 plus 40 plus 10. 30 plus 40 plus 10 is 80. Minus by 10 divided by 2. Okay, so that is our at point C. Okay, you only consider T2 to point C. You don't consider T1 at all because it's a white flag. Okay, so 80 minus 10 divided by 2 times by 10 times by 30 is equal to 22.5 times 10 to the power 3 millimeter cube. Okay, so it's 22.5. Then the next one, we are going to find QZ for point B. So QZ for point B now, we have to include this area over here. Okay. So in that, we know that we have to do 22.5 times 10 to the power 3 plus the width is 20. The depth is 40 plus 10 is equal to 50. The y bar is 30 plus by 50 divided by 2. Okay. So this will be equal to 22.5 times 10 to the power 3 plus 20, 50, 30 plus by 50 divided by 30 plus by 50 divided by 2 times 50 times 20 is equal to 55 times 10 to the power 3. So 22.5 plus by 55 is equal to 77.5 times 10 to the power 3 millimeter cube. And now the next thing is we want to find the first moment of area of point A. So the first moment of area of point A, okay, now at point A is what? Non-thin wall analysis, right? So for non-thin wall analysis, the area that we're going to take, I'm going to highlight in yellow, no, not yellow, in green, is this area over here. This whole area over here that's surrounded by the green. Okay. Oh, no, that's a bad idea. I do apologize. Maybe I should use a red pen. So the area that we're going to consider is this whole area over here. Okay. So when that's the case, QZ at point C will be twice 77.5 plus by the width of what? The width which is equal to 50, 120. The depth is 30. The y bar is 30 divided by 2. Right? So it's 2 times 7.5 power 3 is equal to 155 times 10 to the power 3 plus by 120 times 30 divided by 2, 54 times 10 to the power 3. So 155 plus by 54 is 209. Okay, so it's equal to 209 times 10 to the power 3. Okay. So now we are going to look at point, oh, that's point A. I do apologize, point A. So at point A, right, QZ over T is equal to what? Okay. So at point A, which is at the center, is 209 times 10 to the power minus 9. We change it to meters. Okay. Divide by the thickness at point A is equal to 0.12. So this will be equal to 209 power minus 9 divided by 0.12 is equal to 1.741. Right? It's equal to 1.7. Wait, let me see. Did I? Wait, yeah, 1.742 times 10 to the power minus 6. Okay. Then if we look at point B, QZ over T, right? So QZ is 77.5 times 10 to the power minus 9. Now the thickness at point B is 0.02, right? So 77.5 power minus 9 divided by 0.02 is equal to 3.875. 77.5 power minus 9 divided by 0.02 is equal to 3.875. 3. 875. No. It's not power 96. I do apologize. This is 6. Okay, my conversion was wrong. That's why I look at it like this is way off. So it's 209 power minus 6 divided by 0.12 is equal to 1.741 for 2 times 10 to the power minus 3. 10.5 power minus 6 divided by 0.02 is equal to 3.875 times 10 to the power minus 3. Okay. And then at point C, we have the QZ over T again. So the QZ is equal to 22.5 times 10 to the power minus 6. Divide by the thickness. Now the thickness is smaller, 0.01. So 22.5 power minus 6 divided by 0.01 is equal to 2.25. Okay. So tau max will occur at point B. Okay. So when this is the case, right? When this is the case, we know that at point B, tau at point B, which is equal to tau max, which is equal to, given to us, is equal to 75 times 10 to the power 6, which is equal to V over I. V over I are constant regardless of whether it's point A, B, or C. Okay, V over I. And then the QZ over T, this is equal to 3.875 times 10 to the power minus 3. Okay, so the V over I ratio will be equal to 75 times 10 to the power 6 divided by 3.875 times 10 to the power minus 3. Okay, so 75 power 6 divided by 3.875 power minus 3 is equal to 19.355, right, times 10 to the power 9. And the units is Newton per meter squared. Okay. So therefore, the shear stress at point A is equal to 19.355 times 10 to the power minus 9 bracket 1.742, right, times 10 to the power minus 3 will be equal to 19.355 power 9 times 1.742 power minus 3 is equal to 33.716 times 10 to the power 6 Pascal. And the shear stress at point C, which is equal to 19.355 times by 10 to the power 9, multiplied by 2.25 times 10 to the power minus 3. Okay, so 19.355 power 9 times by 2.25 power minus 3 is equal to 43.549 times 10 to the power 6 Pascal. And okay, so you can see now, like what I've been telling you before, right? This Q over T ratio is critical. Okay, so I've been teaching you all like how to design the optimum geometry by using what? The Q over T ratio. Okay, it's always the Q over T ratio that's critical. Now, I'm going to do something different from the homework. Okay. Now the thing is, what if? Okay, I'm going to copy the whole thing again. The question diagram. What if now VZ? You get what I mean? Right? It's so typical of Eugene, right? Changing something like this, right? Okay. What if it's VZ? Okay. What is it? What? What if it's BZ? Okay, so the first thing that you do, right? And I want you to observe this, okay? You have to